resolution bandwidth. Sometimes they just say RBW, and it's the minimum separation required between two frequency components to be able to visually separate them. I'll show you an example in a few minutes where they merge together and you can't differentiate them because the RBW was too high. Windowing is another term, and it can mean a couple different things. I often use the word windowing when I talk about using the scope's zoom time base, where you're looking at a portion of the time domain waveform. But in the frequency domain, windowing means something entirely different. And I got an example in the next slide. It's a replicating weighted filter to create a continuous waveform from a limited sample waveform to minimize discontinuities at the endpoints, which can cause something called spectral leakage. The next term, spectral leakage, it's errors in the frequency domain waveform caused by discontinuities. Now, I'll show you that in the next two slides. And then gating, I already mentioned that limits the FFT to a user-specified time span. That's a subset of the whole acquisition record. So let's take a look at an example of windowing. Assume this sine wave, I think there's about 5 cycles on screen. It's 5 in a fraction. And assume that's your digitized record captured by the oscilloscope. In order to convert that into the frequency domain, the FFT math function has to replicate that waveform. And theoretically, it replicates it in the infinite negative direction as well as the infinite positive direction. However, notice where I've got the red circles, there are discontinuities at the endpoints because we didn't capture an integer number of cycles. This is what causes spectral leakage in the frequency domain. Those are actually in where those discontinuities are. If you performed an FFT on this waveform, it would see some very high frequency components that aren't actually there. Therefore, what most people apply is they apply a window, and a window, as I mentioned, is a weighted filter. It multiplies that data record, it scales it. And so at the endpoints, it scales it very low, and at the center, it scales it very high. So it suppresses where those discontinuities might occur. Now, the shape of this particular window is, it might be a Hanning. Now let's look at this next slide. There's many different types of windows. The one you see in the upper left is called a Hanning window. There's another one that has a similar name. They call it a Hamming window, H-A-M-M versus H-A-N-N. One that looks similar to it on the far right is a Blackman-Harris. These are named after people that came up with these. It was Mr. Blackman and Mr. Harris came up with a Blackman-Harris. Mr. Hanning came up with Hanning. Now the one in the center is a triangular. It's not named after anybody. It's named after the shape. The one in the lower left, flat top, that one is supposed to have provide the most accurate amplitude accuracy, but not so well. It doesn't provide very good frequency accuracy. And so each of these different windows have different results in accuracy, in perhaps better amplitude, better frequency. The one on the lower right is called a rectangular window. That's basically what I showed in the previous one if I applied no window at all, no scaling, a rectangular window. So let's take a look at and compare a couple of windows. So here I'm showing 2 cycles of a 1 megahertz clock signal, and the one on the left is using the Hanning window. Now here you can see the frequency peaks don't look so much like spurs or distinct tones. This I would call lobes. They're beginning to spread out. We don't have much frequency resolution on this particular waveform. And the reason is we only have 2 cycles on screen. The one on the right is using a rectangular window. It actually has higher frequency resolution. However, take a look at this next slide. Now I've rescaled the time base of the time domain waveform, and instead of exactly 2 cycles of this clock signal, now we have about 2 1/3 cycles. And so we've created these discontinuities at the endpoints of the waveform, and the one on the right is beginning to fall apart. And if I vary that time-based setting and say capture 2.4, 2.5, you'll get all sorts of strange shapes if you're using that rectangular window, and lots of errors, and you're just going to get very poor results. This is an example showing how you probably should scale your time domain waveforms if you want to get better resolution. So both of these images are using the Hanning window, and I probably should have mentioned before, if you're not sure which window to use the Hanning. It is the most general purpose, and on I believe most, if not all scopes, it is the default window that gets turned on when you use FFT. So the image on the left, I'm showing the 2 cycles. You get what's the lobe looking shapes for each of the frequency components. It's kind of spread out. You have poor frequency resolution. The one on the right, I have 20 cycles displayed on screen, and you can see these lobes become much, much narrower, and now you have more distinct peaks of where the frequencies are, and so you have higher frequency resolution. Now this is an alternative you have. Now on both of these I'm showing Hanning window for both. Alternatively, you can scale the vertical linearly as opposed to logarithmically. The default is the vertical scaling on an FFT is typically scaled logarithmically, and it reads out in units of dBm or dB volts. The one on the left I'm showing is I have selected the linear scaling. The effects are it suppresses those peaks, makes them look lower, and it also suppresses the noise floor, which is kind of nice. But if I was trying to measure the amplitude of some of those peaks that are far out there, I just couldn't do it because I don't have enough amplitude resolution. The advantage, though, is of the linear scaling on the left is it measures out in volts as opposed to dB volts or dBm. And people that work in the time domain often relate to voltage as opposed to dB. But on the logarithmic scaling on the right, I have lots of resolution on measuring those peaks. Now, this is perhaps something we might all be able to relate to, linear versus logarithmic. When I started creating this presentation a couple of months ago, I saw this graph for the coronavirus cases and the coronavirus deaths in Malaysia. And so you may not be able to see the time scale there, but I think the last date was sometime in February. That's when I started creating this. And I was seeing some graphs, people showing it, the cases and the deaths on a linear scale, and the number of deaths was way down at the bottom. You had no resolution, you couldn't see it. This is showing a logarithmic scale, and I can see both the number of cases and number of deaths on the same scale. So maybe you can relate to that. Now, what about measurements? How do you perform measurements on the FFT? Number one, you have cursors or markers just like you do in the time domain. You can do frequency peak search, and so you can have it automatically find where those peaks are and give you those amplitudes. We have a relatively new measurement in InfiniiVIsion scopes called Y at X. So Y means the vertical axis amplitude, X is the horizontal horizontal axis, which could be time or frequency. And so you can measure the amplitude if you know what the frequency is. Tell me what the amplitude is at this particular frequency. There are some advantages to that measurement, and we'll show that in a few minutes. And then there are several other custom RF measurements that we've implemented into our scopes. You'll typically see these in spectrum analyzers, but not in most of our competitor scopes, but they are in the InfiniiVIsion scopes. Channel power, occupied bandwidth, adjacent power ratio, and total harmonic distortion. So here's an example of frequency peak search. Now, if you look up at the top of the display, you see those white triangles. Those are automatically finding these peaks, and they're based on a threshold level that you can set. As you can see, it found the fundamental third, fifth, seventh, and ninth harmonic. It didn't find that 11th harmonic because it was getting down there too close to the noise floor. Now, this is logarithmic scaling. If I was scaled linearly, it would probably only find the first two peaks. Now, if you look over on the right, that's where you can see the measurements, and it numbers them 1 through 5 to show you what each of those are measuring in frequency as well as amplitude. You can reorder that in order of amplitude. It's possible you could have one of the higher harmonics higher amplitude than the lower harmonic. So you can reorder those. This is an example of the Y at X measurement. I've got it circled there in the middle. And so I was unable to measure that 11th harmonic. And so I was able to, I knew what the frequency was, is the 110 megahertz. So I set up a measurement. What is the amplitude at 110 megahertz? And it measures specifically that. Now, another advantage is that measurement is just like our other parametric measurements, like rise time, fall time, volts peak to peak. You can get statistics of those measurements. So you can get mean, min, max, standard deviation. And I also have displayed on there total harmonic distortion as well. Now let's switch over and let's do a demonstration of FFT. And if you're brave enough, you can do this demonstration as well. Okay, David, can you see that display?
I can see the display.
Okay, I'm going to assume you can. I'm going to go ahead and do a default setup and start over and show you where I get this signal. And so I'm going to press the help button. And then there's a soft key that says training signals. This webcam is not that good. You may not be able to read it. But this is the list of all the training signals we have. We have one that says square with sinusoidal noise coupling. So I'm going to select that one. Let's set up our scaling. And I'm going to rescale this waveform and put it down. Let's put it up here near the top of it. And so I've got, I don't know, 10 cycles of this clock signal. And as you can see, it's got some what looks like noise. Some people might call it crosstalk writing on the top of this. Now, maybe we don't know what's going on up there. So I'm going to select the math button. And then the default, it comes up plus or sum. So it's right now it's adding channel 1 and channel 2. I'm going to change the operator to FFT magnitude. Now there's the FFT of this waveform. It automatically sets a span, center frequency, and it sets the scaling. I'm going to rescale it. Now over here on the right, near the math button, there's a knob at the top where you can change the vertical scaling, just like you can do on the oscilloscopes vertical scaling in a time domain waveform. You can change the vertical scaling on the frequency domain waveform. You can click it and get a fine adjust. Again, just like you could on the time domain waveform. And the lower knob is the position. So I'm going to position it down here at the middle so we can see it more clearly. Now, this webcam is probably just showing a white smear all the way across here, but I can see very distinct vertical lines. So it's showing tons of harmonics way out here. And then it's showing one that's just jumping right up. That's what's going on up here. Let me move this guy over to around center screen, and I can do that with this selection here that says center frequency. The default, when I turned it on, it says 200 kilohertz. So I'm going to press that, and I'm going to slide this over to till that particular peak. Whoop, is right about center screen. Now you probably can't read it, but it says it's around 89 kilohertz. So something around 89 kilohertz is coupling on there. Now we're going to come back to this guy in a minute, but let's look at some of these harmonics up here a little closer. I'm going to change my center frequency to about 20 kilohertz. So it shifts it over. And I'm going to take my span and I'm going to spread it out. So that says 500 kilohertz. Now it's 200 kilohertz. Now it's 100 kilohertz. Now it's 50 kilohertz. So from the left side of the screen to the right side of the screen is 50 kilohertz in frequency span, and the center is at 20 kilohertz. Now, I also have the option of setting a start frequency and a stop frequency. This is minus 5 kilohertz, so of course you can see nothing over there. It has no negative frequency. And the right side of the display is 45 kilohertz. So let's go back to span though. So this peak right here is the fundamental of this clock. The second one is the third harmonic, fifth, seventh, so on, and we can see there are tons of harmonics. And as I mentioned earlier, an ideal clock signal or square wave has an infinite number of odd harmonics. Let's measure this one using the cursor. So I'm going to press the cursor key, and I'm going to change it from manual cursors, which means I can independently control amplitude cursors and timing cursors, to track waveform, which means well, you'll see in just a minute. So I'm going to change the source to math, and now I'm going to adjust this X1 cursor and make it land right on the top of this waveform. And so when I adjust time, the amplitude cursor tracks, moves along with the waveform. Now I'm going to adjust the X2 cursor and set it on top of the third harmonic. Now over here I can read the X1 cursor is at 1 kilohertz. So this is a 1 kilohertz square wave. The amplitude is minus 8.8 dB volts. The third harmonic, X2 cursor, as you would expect, is 3 kilohertz, and the amplitude is minus 18.6 dB volts. Now let's turn off the cursors, and let's measure another way. Let's turn on search. So there's a search button up here near the horizontal knob. I'm going to press that. And then over here, it says, well, what do you want to search for? And you can search for edges, pulse width, rise and fall times, runt. So this is violation search. So looking for a violation of rise time, fall time, or look for runts. These are all time domain searches. Here's one called frequency peaks. Let's select that. And so now you can see white triangles up here, And this is pointing to the fundamental and the third harmonic. And over here, you can read it. It says 1.001 kilohertz and 3 kilohertz. And it's reading the amplitudes about what I was doing with the cursors. Now, what about all these other harmonics? Why isn't it automatically finding those? That's because, well, number one, I can maximum number of peaks. Right now, it's looking for up to 8. I can go up to 15, but it's still not finding them. What I need to set up is threshold. Now, as soon as I touch the knob, you can see the threshold is up too high. If I get the threshold down here where all these peaks are, then I can see all 15 of the harmonics and measure all of them automatically. Now let's go back into the FFT menu and let's change from logarithmic display to linear display. So there's the linear display, and you can see now it's only finding one peak, but it's measuring out in absolute voltage. It says 368 millivolts. If I go back to the threshold, well, I think I need to set up excursion as well, but it's going to be very, very difficult to get these way out here. So again, that's the advantage of using linear or logarithmic scaling on the amplitude. Let me rescale this now. Okay, now let's rescale the time base, and let's go down to just 2 cycles. There you can see the lobes. And so as I scale more cycles, I get better frequency resolution, less cycles, poor frequency resolution. Now let's compare windows. So I'll go back well, I'm already in the FFT. Over here is where you can select the various windows: Hanning, flat top, rectangular, Blackman-Harris, and Bartlett. Let's select a rectangular window. So again, now we've got a little higher frequency resolution. Over here on the right is where you can read out what the RBW is. It says it's 500 hertz. With Hanning, 750 hertz. So the lower the frequency is, the better. So the rectangular gave me better frequency resolution. Those lobes became a little sharper. But watch what happens. Now I've scaled on some partial cycles, and the FFT waveform is just kind of falling apart with the rectangular, whereas if I go back to Hanning, it looks good again. Now, my recommendation, if possible, is scale more cycles on screen like you see here. Now, let's go back to that big peak we saw earlier. Now, by the way, you see something jumping in here? That's probably my cell phone or Bluetooth or something going on that was causing that disturbance. But anyway, that's interesting. So anyway, let's go back. Remember that spur occurred at 89 kilohertz. Let's go back to 89 kilohertz. That's 89 hertz. Let's do 89 kilohertz. There is that crosstalk that's going on there, along with some of these higher harmonics. I'm going to scale it to 10 cycles now. Now let me show you gated FFT. What gated FFT is, I can say, I only want to perform the FFT on a narrow portion and so this is my zoom window expanded out. So now you're only looking at the crosstalk. Let me change my span here. Oh, I haven't turned on FFT yet, or a gated FFT. Now let's turn on gated FFT. And now it's only looking at the crosstalk. It's not looking at anything else. And so all those harmonics are gone. So that's a gated FFT measurement. It's pretty easy to set up. I've got an application I'm going to show you soon, and I better get moving along because I'm running out of time, of an application of measuring sidebands with gated FFT. So let's go back to the slides. And let's walk through a couple of these applications. Now, this first one here, extracting crosstalker noise, well, I say demonstrated in video. I demonstrated it live for you. We'll take a look at characterizing output ripple on a power supply, control loop response test, which we'll go into deeper in a couple of weeks on another training session we're going to have, current harmonics, gated sideband measurements, and jitter analysis. We may not get through all these. I may skip a few of them because of time. So here's an example of characterizing the DC output of a switching power supply. That yellow waveform below is the time domain waveform. That's DC, even though it doesn't look like DC. That's what DC looks like from a switching power supply when you zoom into it. There is about 20 millivolts peak to peak output ripple. This is, as you can see, I've got my voltmeter turned on up here, my DVM. You can see it's measuring 4.98 volts. This is a 5-volt power supply. But you can see this ripple that's happening at 2 megahertz. That's the switching rate of the power supply. But also look, there's all sorts of fuzz, or what looks like noise, riding at a much higher frequency than the 2 megahertz switching rate. And so I've turned on FFT to see if I could uncover what's going on this power supply. You can see the first peak here is the switching rate. The second one is kind of jumping around a little bit. Maybe, I don't know if you can see it, but it's around the third harmonic, so it's around 6 megahertz. But what's happening here is we don't have very good frequency resolution, and there could be 2 frequency components merging together, and that's exactly what's happening. I'm not performing this measurement that you're seeing here properly. I don't have enough cycles scaled on screen. I've got 1, 2, 3, 4 cycles scaled on screen, which means I'm not getting much frequency resolution. And so now I don't know how many cycles I have. I have a bunch of cycles scaled on screen. Now, I can't see in detail the time domain waveform very well, but I can certainly see it in the frequency domain. And so you can see these, this one is actually, I think, a second harmonic. There's the third harmonic, but here's something that popped up that's unexpected. It measures, I can see over here, it's 6.78 megahertz. That is not a harmonic of this switching rate, but what it is what I was probing was a wireless charging system that has a resonating frequency at 6.78 megahertz. So it was coupling into the power supply, and with the FFT, I was able to uncover it. This is an example of our Bode plot capability, which we'll go into deeper in a couple of weeks. And you can see at the beginning of our sweep, when we're measuring gain, I'm able to measure 53 dB. Now, a lot of people say, no, scopes can't measure anything that with that much dynamic range. Actually, our Bode plot capability, we specify up to 80 dB. I've been able to measure in a low noise environment upwards of 100 dB. So that's pushing what a network analyzer can do. Um, but how do we get that dynamic range with the oscilloscope? This next slide shows you. When we're measuring gain, what we're measuring is a ratio of output divided by input. My yellow waveform here is my input waveform. It looks like noise. This is actually all that, this is output ripple is what it is. But I've got a test signal riding on top of it at 100 megahertz. And what I'm trying to measure is the amplitude of this test signal. This is we do it in the frequency domain, and I've shown it on a linear scale, just so I could show you the absolute voltage. This 100 hertz peak on VN, you may not be able to see it, but it's measuring about 100 microvolts. That's impossible to measure in the time domain, but in the frequency domain, I can measure that. This image over here on the right is measuring the amplitude of the green waveform, where the noise is relatively small, and it's measuring about 43 millivolts. So if we take the ratio, the gain in dB, 20 log 44 millivolts divided by 102 microvolts is 53 dB. So that's how we can measure specify up to 80 dBs, because we do it in the frequency domain. You have more accuracy, more resolution in the frequency domain. This is another example of frequency domain measurements. This is a current harmonics measurement using our power supply software app. This is something required of many products. Um, the green waveform is the current going into a power supply, and because of full wave rectification, the current waveform is not a sine wave. It's a pulsed waveform. And when you've got a product plugged into the mains or to the line, the socket on your wall in your house or in your factory, it starts pulling current out of the mains. And if it's pulsed current, like most products are, it can disturb other equipment that are connected to that same circuit. And so there are specifications on what's called current harmonics. And so this is an example of, we run an FFT on the current waveform. So we're using a current probe. So this would be something difficult or impossible with a spectrum analyzer, because they don't measure current. And in the table up above, we can measure the amplitudes of all those peaks up to the 40th harmonic. The second column shows the amplitudes. The third column shows the specification. It's a European specification. It's called the IEC 61000-3-2 specification. And if people in the US or China want to sell our products into the EU, we have to meet these specifications. So we can do this automatically and give you pass-fail indication if any of these harmonics fail. This is an example of a gated FFT measurement on NFC, near field communication. It's a very complex RF signal that has amplitude modulation. And there is one particular measurement that's required for compliance on measuring something they call load modulation amplitude. If you look on the left, I've got the zoom window bracketed around a narrow portion of modulation, and you can see it. It looks like amplitude modulation. The original specification for NFC called out performing this measurement in the time domain. The problem is this modulation can be very, very low, as low as just a few millivolts of modulation. And it was very difficult to measure this with any accuracy or resolution. And I'm showing you the method that we originally used. There I'm using a waveform math function called envelope, and then some filtering to filter out some of the noise in an attempt to measure the amplitude of that modulation in the time domain. About 2 years ago, they changed the test methodology required for this measurement, and now they they specify measuring it in the frequency domain based on um, sideband modulation amplitude. And so that's what I'm showing in the right side. There you can see we're measuring an amplitude 11.3 millivolts with much higher resolution. Um, we got 2 minutes left. We're doing okay. Here's another example of uh, what you can do in the frequency domain that's very difficult in the time domain, and that's jitter analysis. The yellow waveform represents, it's a serial stream of data, and what we're doing is we're using the jitter analysis capability in our 6000 series scope. It's able to do a clock recovery and then measure the error of the placement of each edge of that signal. Now I'm zoomed way out, and there's probably hundreds of edges in that signal. The purple waveform in the middle that you can see a sinusoidal shape to that looks noisy, what that waveform is we call that a jitter trend plot. Now, TIE stands for time interval error. It is plotting the error, timing error of every edge placement of the digital serial signal relative to the recovered clock. And so that's why it looks like noise. It may actually be a Gaussian distribution of timing error on each of those edges, but you can also clearly see that sinusoidal shape to it. That means there is some periodic jitter, perhaps caused by something else. And the waveform on the bottom is the FFT trace run on the jitter time interval error plot that can very quickly tell you what that periodic jitter is. So to review what we've discussed today, FFT uh, transforms the time domain into frequency domain, and it can go the other way around. The frequency domain trace shows sine wave frequency components that make up the time domain waveform. All waveforms, all signals are composed of multiple frequency components of sine waves. FFTs can sometimes uncover, show you things that you can't easily see in the time domain. Signals buried in noise can often be measured much more accurately and with higher resolution in the frequency domain. And my bottom line recommendation is don't be afraid to look in the side door for a different perspective. Now, someone that more often uses spectrum analyzers, they work on RF signals, they would say looking at the frequency domain is looking in the front door, and looking at a time domain waveform is looking in the side door. It all depends on your perspective. These are some various application notes we have, and David can provide you with these slides, and you can download these publications later. The last one I have listed there, it's actually from one of our competitors, National Instruments, but I thought their white paper did a pretty good job of explaining windowing. And so you could just Google that and be able to download NI's white paper on that particular thing. I believe you're all pretty familiar with the Keysight InfiniiVIsion scopes. All of them have FFT capabilities, including the entry-level 1000 series. Gated FFT is available on the 3000, 4000, and 6000. It's not available on the 1000 and 2000 series. Jitter analysis, that last app I showed you, is only available in the 6000 series. The frequency response analysis Bode plots I showed you is available on all the scopes except the 2000 series. And in fact, frequency response analysis or Bode plots is standard on the G models of the 1000 series. So at this point, David, I'd like to turn it back over to you to see if we have any questions. You there, David?
Yeah, but I didn't see any question in the chat window, so I think it's good. Yeah.
Okay. Any verbal questions for anybody? Okay, next Thursday, I'm going to be covering competitive, and I'll be showing some side-by-side measurements on a Rhodian-Schwarz oscilloscope versus the Keysight 4000 series. Now, I did a DTE training about a month ago, I think, where we had very limited time, and I was only able to show one demo. Next week, I'll show additional demos side by side of the Keysight 4000 versus the RTA. I think it's the RTA 4000. So anyway, thanks for attending today, and hope you come back next week. Talk to you later.